Record. Okay, so again, we're continuing the theme of collecting areas, integrating with respect to x or y. That's going to give us a volume. Here I have -4 times the sine of x. And what I want to do with this one right here is it still has a period of 2 pi. So over here, this would be pi, finishes its period here at 2 pi. I want to take this chunk of the sine right here, and I want to revolve it about the y-axis. What am I going to get when I do that? Well, it's going to make kind of half of a donut. And so I'm going to try to draw my best half a donut here. So I'm going to have these two humps, and it's going to come around. Oh gosh, something like this. Oh man, that's awful. Let me try that again. Some days are better than others. And let's use blue. All right, so we're going to have the big outer circle. There's going to be a hole in the middle, and it's going to have, I guess that's not much better either, kind of like an inner tube kind of shape, but it's flat on the bottom. Gary needs to go back to art school. So think about what we've been doing to make that happen. We have been using discs or washers to make that. So we would take a slice like that. To figure out the length of that slice, that's the difference between two x values. x2 over there and x1 over there. Problem with that, that means I have to solve for x, which means I have to use an arc sine, and it wouldn't be a function, so I'd have to have a separate arc sine for this side than for that side over there. I don't think I want to do that. So here's what I'd like to do instead. Undo that thought. And instead, imagine taking a slice that way and revolving a bunch of those slices. Right? As I revolve them, they're going to generate cylinders, and when I put all those cylinders together, it's still going to make the same shape I have there. So if I take that and revolve that around, right, what it's going to make is a big cylinder, whatever that height is right there. And the radius to get to there is whatever x value I happen to be at there. Well, that's just the radius, right? So once we spin that, that's going to generate for us a circumference. Oh, okay, I get from pi. Yeah, so those, I'm only going to choose x values between pi and 2 pi. Yeah, so yeah, we'll get to that part in a minute. But any one of those is going to look something like this, and we're just going to stick them all together, and eventually it'll make this weird kind of donut over there. And a cylinder like that, when you unroll it, is just a rectangle. And the base of that rectangle is just the circumference of the cylinder times the height. That's the area of a cylinder. So the area that I want to add up here is the area of a cylinder. And that's going to be 2 pi r times h. So all I have to do in the picture is figure out what is h and what is r. Well, I already determined looking at the picture that r is x, and the height is the y value, and the y value comes from that function right there. So then my areas must be 2 pi times a radius of x in this case, times a height of -4 sine of x. So that's the area of one of these cylinders. If we put a dx on it, well, that would be the thickness of the paper there that we're making the cylinder out of. So if we take our area times a little thickness there, we're going to get volume. Okay? All we have to do is add up all those volumes. So for this one right here, I can just modify that Squeeze it down here. So my volume will be the integral as x goes from pi to 2 pi. We can pull out some constants there. So I think I'll pull out negative 8 pi. And then what's left is x times the sine of x dx. And if I can integrate that, then I can find this volume. Slight catch on this one. X times the sine of x is the result of some kind of product rule. I did show you a couple weeks ago a kind of double substitution that you can do. I'm going to skip that for now and talk about that later in the course. For now, we can just use numerical integration to come up with that. So we can just plug that into Desmos, and that's going to give us the volume that we want. Alternatively, if I tried to use the disk or washer method, I would have two different arc sines that I would have to subtract, and that one's way harder. It's doable numerically, it's just harder to set up. Okay, so we're going to skip that way and just look at it this way. So this right here is what we call the washer method. Sorry, no, the shell method for finding volumes. And I had sent out an announcement with kind of a summary of how the different methods are related. So let's take a quick look at that. So this is a nice cheat sheet. So what it does is I broke it down into whether you have a vertical axis like y in the first column or a horizontal axis going around x in the other column, and then how the setup would be is if you were doing washers versus shells for each one. So these are the 4 different scenarios that you can end up with. A note on the bottom about the radius functions. Typically, the radius function is either just x or just y when we use the shell method. And sometimes one's better than the other. Sometimes it doesn't matter. Sometimes one is a mess. Sometimes, again, they're pretty similar. So let's just try a couple problems.